Hi, my name is Itamar. You can find lots of articles I've written about Python performance and other issues at pythonspeed.com. I work as a consultant. I've written some software tools. And this is a talk about priorities. What should you do first? What should you do second? And so before we start talking about software performance, the sort of thing you should be thinking about even before that is whether or not the software you're writing should exist at all. If your software you're working on hurts people, if the software you're working on damages the environment, then if you make your software faster, then you're just causing damage faster. And so before you start thinking about should this software be faster, you should be thinking about should this software exist at all. And if it shouldn't, then you can go find a different job, and then in that new job, you can think about software performance. So I'm going to assume that you're working on something very useful and great, and I hope you all are. And now I'd just like to set the scene. So software performance, software speed is a very situational kind of thing. If you think about a web application, you want it to be very responsive. It's about how quickly you get back a response, how quickly you interact. And often the bottlenecks involve how the user interface works, how interactions in the browser work. On the back end, the bottlenecks are interactions in the database. And that's a web application. That is very different than what I'll be talking about today, which is data processing. And so what I'm talking about here is within a very specific domain, and some of the really deep underlying principles you can always translate, but you always have to think about what your particular goal is in a particular situation. So what I'm talking about today is data processing, a lot closer to the topic of this conference. Things like scientific computing, things like data science when you're processing the data. And more broadly, the class of tasks where you read in some data, you do some sort of processing and write out a result. And even more specifically, I'm talking about software where the CPU is the bottleneck. If you, again, are talking to a database and all your interactions are SQL queries, the way you'll make your software faster is by optimizing the SQL queries, adding an index. It's not what I'm talking about today. Today, we're talking about code where the computation you're running, or maybe memory writes, but the actual computation you're doing is the bottleneck. And that's sort of the constraint of this discussion, the scenario we're talking about. The specific problem we're talking about is slow software. And slow software is ubiquitous, and it comes with a whole group of different problems that result from this underlying issue. So if your software takes a long time to run, then development can be very difficult. You want to try a new version of your algorithm, but it takes an hour to see whether or not it's better. So now you can do at most 5 or 6 experiments a day. And that can really slow down how fast you improve your code. If you get down from 1 hour to 5 minutes, then now you can do things much, much faster. If you have users using your code, once it's in production and they are waiting for responses, if the software takes too long to get a response, they will be unhappy. The faster it is, probably the happier they'll be in most situations. Not always, sometimes it doesn't matter, but in general, people are happier when they get results back faster. If you're running your software at scale, you're going to end up paying higher bills for running your software. If you're scaling up, you have thousands of users, you're running on lots of computers. If you have to support more people, then now you have to spend more money on computers or cloud computing. And finally, since everything here is running on electricity, if you're using source of electricity that is non-sustainable, the more computation you do, the more electricity you use, the more CO2 emissions we have. And data centers in general are an ever-increasing percentage of global CO2 emissions. So it's nice to use less resources. So that's our problem. Our software is slow. So how are we going to solve this? So one theoretical solution is say, well, we have some algorithm. It runs on one CPU. We can just buy a faster CPU. And here I'm talking just about the speed of a single core, so the speed of a single thread that's running on your computer. And there's a company called Passmark, and they have people run benchmarks on lots of different CPU models. So look at the numbers for CPU in my computer. It's probably a couple years old at this point. And on their benchmark, it's 4050. Higher is better in this measure. So the higher the number, the faster you are. And in their database, the fastest single core CPU, that is a single thread speed, is that recently released Apple M3 Pro. It's 4800 compared to 4050 for my CPU. So it is basically not possible to buy a CPU that is much faster than this on single core speed. Like, you just can't. It doesn't matter how much money you have. If you have a really ridiculous, I'm sure if you had like $10 million, you could get something, but it would be like 10% faster or 20% faster, 30% faster. There's a very hard limit. So getting a faster single core CPU is just fundamentally not workable. It's not a viable solution. This is not going to work. So the next thing we can consider is, well, let's use parallelism. Right? My computer has something like, depending how you think of it, between 10 and 12 CPUs. Some of them are not quite as fast as the others. And so we can see, again, the benchmarks. And you can see that previously it was 4,000 for a single core. Once I'm using all the cores on my computer, if I have a parallel program, I get up to around 35,000. So it's a lot faster. And in the database of this benchmark company, Passmark, there's one CPU that has, it's like 5 times as fast as that. And my guess is that there are actually CPUs that are faster than that they just don't include because they're not really available to consumers. But if you're running a cluster, you can get probably even faster CPUs that have lots and lots of cores. And as long as you can run in parallel, you can just go faster. So here, you spend more money, you get 5 times as fast. It's great. On my computer, I can just scale up to all the CPUs. I'm going faster. That's great. So that means is multi-threading, multiprocessing, running your code in parallel is a great way to speed up your code. And then a third way to speed up your code is optimizing your software. That is somehow changing your code so that it runs faster on a single core. And then if it runs faster on a single core, if you run it in parallel, that will also be correspondingly faster. But there are some caveats here. If you're using NumPy or SciPy or Pandas or any of these libraries you're likely to be using in Python, your code that you're running is written in C or C++ or Rust or Fortran. And they're all quite fast, much faster than Python. That's why you're using NumPy or SciPy or Pandas. And that being the case, that suggests that there isn't much more you can do to make software faster. You've gone from slow Python to fast C. Now your code is fast, and is there anything more you can do? Unclear. And so at this point, lots of people conclude that the way to move forward is parallelism. We know we can't get faster single core CPUs. It's just not commercially available. There's hard limits on current engineering technology. You can, however, get CPUs that have lots and lots and lots of cores. You just throw money at the problem, you'll get a machine with lots more CPUs. And those are both facts, and they strongly influence how we write software. And then there's an assumption that optimizing software is not possible. And as we'll see, I think that is often not the case. And so the conclusion is that if your software is slow, you should immediately switch to multi-threading, multiprocessing. You need to switch to parallel programming in order to go faster. And so the rest of this talk is a counter-argument against this way of thinking. We'll start by talking about why focusing only on parallelism can be a problem. I'll argue that your software probably can be optimized, even on a single core. You could probably make it run much faster. And what that suggests is you should first optimize your software, first try to make it run quickly on a single core. Then, once you've spent the effort on that, you should focus on parallelizing it. And so we'll start about talking about some limits to parallelism, why it's not as good a solution as you might think. So first, and this is sort of a fundamental limit, some algorithms cannot be parallelized. And sometimes this is in full. Sometimes there's just no way to make the algorithm parallel just because of the way it processes data. Every piece of computation depends on other pieces in your data set. And so you can't split your data set into two chunks and process them in parallel. Sometimes you can only parallelize part of the algorithm. There's Amdahl's law, which is a way to calculate the resulting performance of your code if you can only parallelize part of it. This is all very domain specific. It's all very algorithm specific. It's very difficult to say in abstract whether or not your code is parallelizable. But sometimes it just isn't. And when it isn't, there are workarounds. In particular, even if the algorithm can't run in parallel, if you have to process 100 files, and those files can be processed independently, then you can run a single-threaded algorithm on multiple files in parallel. So file 1 is on one core, file 2 is another core. So even if the algorithm is in parallel, you might still be able to get parallelism. So it's not as big a constraint as it can be. This assumes, though, that you have multiple inputs. If you just have one giant input that you can't split up, then you're stuck. Another limit is that parallelism doesn't reduce costs. And here I'm talking about like monetary costs, financial costs, the cost of the hardware that you're using to run it. If you were to make your software more efficient, if you were to optimize it, make it run faster, that has two benefits. You get results faster. So instead of taking an hour, maybe it takes 10 minutes. And also you're using less computer time, which, as we'll see in a second, can save you some money. And parallelism can only give you the first benefit. If you're using multiple CPUs, that is giving you results faster, and that's great. But it's not reducing how much computation you're using, which means the monetary cost of running the computation doesn't go down. And we can think of this in two scenarios. So one is you have your own computer under your desk or a laptop that you're running your computation on. So you can look here are the performance numbers, the benchmark I showed. Again, for the i7 12700K is a CPU in my computer. It costs about $400 to buy this CPU. Plus you have to buy the rest of the computer. Just focusing on the CPU. If I run in a single thread, I'm running at speed of 4,000 based on this benchmark suite. If I use all the cores and I run in multiple threads, it's 35,000. So great, I'm running 9 times faster. And either way, I spend $400. Right? So parallelism in this case is great. It is actually saving me money because I can then go on and run some more. If I want to go faster, I need to buy a more powerful CPU. And this is when things start getting a little more expensive, because you'll notice that this other CPU, this is the fastest multi-core CPU in this particular database. You can buy it. It costs $10,000 just for the CPU. All the RAM and whatnot will cost you a lot more. And you'll get a 5 times speed up. But the jump in price from $400 to $10,000 is not 5 times as much. It's 25 times as much. So you're running 5 times as fast, but you're paying 25 times as much. So it's a big jump in costs in order to go faster. And so at some point, like you start spending a lot more money to get more parallelism on a single CPU. And you can build a cluster out of cheaper computers, but now you're dealing with a distributed system and your programming job just got a lot harder. And the other scenario here is cloud computing. You're renting time on the cloud from AWS or Azure or Google Cloud or one of their competitors. And here your costs, the first approximation, scale linearly with the number of cores. So you don't really have the issue of these sort of giant jumps in price. So if you want to run 5 times faster, you're going to spend 5 times as much money. Right? You get 5 times instead of 2 cores, you go to 10 cores. And now the virtual machine you're renting in the cloud is going to cost you 5 times as much. If you want to run 5 times faster, but just optimize your software, if you can figure out some way to make your software 5 times faster by some of the techniques we'll discuss next, you're running 5 times faster at no extra runtime cost. And if you're only running your software once, You don't want to do this, right? If you're going to run process a data one time, you just rent a rent a virtual machine in the cloud with 40 CPUs. It runs really fast. You spend $20. You shut it down. You're done. Problem solved. But if you're scaling up, if you're running your batch jobs at a larger scale or continuously, then parallelism is not saving you any money. It's just moving the costs around. Whereas making your software faster can actually reduce your costs by reducing how much CPU time you need to use. So parallelism is not perfect. It's very useful, but it has some limits. And so next we'll see just at a very quick overview of the ways in which it is actually possible to make your software faster. And software performance comes from multiple levels of the way you write your software. At the highest level is the architecture, and then there's the algorithms. There's just optimizing your code so it doesn't do unnecessary work. You can tune it for modern CPUs. And each of these levels you probably want to address in order of priority. Like architecture has the biggest impact, then algorithms. So again, a large part of how you get performance is how you prioritize your work. And if you have a good architecture, you can get speed ups that would be impossible with a bad architecture. And only have 25 minutes, so can't go into depth on any of these, but I can at least give some examples. So if you're processing data frames, you have a number of libraries. The most popular one is pandas, but polars is a new contender that has been gaining a lot of users recently. If you're not familiar, if you never use these, the basic data model they're helping with is columnar data that has type and a name. So basically a spreadsheet kind of data. So you have different columns of different types and you're processing them. And if you're using pandas to process your data, every time you tell it to do something, it does it immediately. So you say, I want to sum this column, it will sum the column and give you the result. I want to load this file, it will immediately load the data into memory. I want to filter the rows with this criteria, it'll immediately filter the data. And polars, which is also has a mode that works like this, eager mode, but it also has a lazy mode. And in polars lazy mode, it doesn't actually do the work immediately. Instead, you have to give it all the things you want to do, and then you say, okay, this is all the steps I want you to do. Now actually do the work. So you say, I want you to load the file, and then filter it, and then summarize it, and then group it by this column. Okay, that's everything you're going to do, and then output it here. Now that's everything you're going to be doing. Now go and do it. And what that means is polars knows your plan end to end. It knows your goal. It's not doing step by step what you're telling it to do. It's trying to achieve the equivalent of what you told it to do. And so it can say, okay, this is what you want me to do. I can optimize your code, I can optimize your plan and come up with something that gives equivalent results, but it's faster. This is, for example, how a SQL database works. When you do a complicated SQL query, the database will figure out via a set of heuristics what things to do first so that it gets you the results as quickly as possible. And just to give a sense of what kind of optimizations you do, if you are filtering rows, that means any row that you filter out, there's no point in doing any processing on because you're throwing it away. And so Polar's query planner will try to move all the filtering as early as possible in its execution plan so that it drops all the data as soon as possible. So any steps later on that are more expensive only happen in data you actually care about. And it does this for you automatically if you're using the lazy mode. And so there's a fundamental architectural difference between pandas and Polar's lazy mode. Pandas architecturally cannot do this. The whole way it's designed is to do whatever you tell it immediately. And so there are performance improvements that Polars can do that are impossible in pandas. And this isn't like Polars also does parallelism, which is very nice, but this isn't about that. This is even on a single CPU. By just being smarter about how it's architected, it's able to give you performance benefits that are impossible with a different architecture. And so next, let's look at an example of algorithmic speedup. So obviously, you want your algorithms to scale, and so this is part of your design criteria, but it's also easy to accidentally write code that is non-scalable. In particular, accidentally quadratic algorithms, where the runtime is the square of the length of the input, n squared, are very common. There's actually a blog called Accidentally Quadratic you can read. It has many examples. And this particular example is taken from there. So in the Mercurial version control system, someone noticed that some code was slow, and then they figured out they were basically trying to find the overlap of two lists, which takes square of the length of the lists. And by switching to one of the lists to a set, they got the runtime down from 18 seconds to 1.3 seconds, this particular task. And so you'll notice it's only 5 extra characters. And so someone typed 5 extra characters, and now their code is running 15, 16 times faster. Right? And it's not like this happens every day, but it is a real issue. Accidentally quadratic code is actually quite common. And so if your algorithm is n squared, if it's not scalable, it doesn't matter how many CPUs you throw at it. It doesn't matter that you're using C instead of Python. Like, if you have 10 times as much data input, it'll take 100 times longer to run. It's just not going to scale at all. So using the right algorithms can give you really massive speedups. So you have a good architecture, you have a good algorithm in terms of scalability. There's still a lot more you can do. So this is rescaling intensity is a very common thing in image processing. It's just changing the contrast. Like every time you take a photo on your phone and you like drag around the contrast slider, you're doing the same thing. Your phone's trying to do it automatically for you when you take a picture. So scikit-image has an implementation. And if you optimize it a little bit, you can make it around 4 times faster. And if you write an optimized version of the lookup table, which limits you to 8-bit images, but it's that much more faster. And these are all ON, they're all linear runtime, but the constant multiplier, how much it takes to write in each step is much, much lower. And so you get a really significant speedup. And this is a lookup table version just so you can see it. So it's really not that much code. You just, and it could probably be even faster. This is mostly written for educational purposes. So not very much code, and you get a really huge speed up by just figuring out that you were just calculating the same thing over and over and over again. And if you just cache it in your lookup table and only calculate it once, suddenly your calculation is much, much faster. As an aside, I just mentioned that the version scikit-image open source library is slow. I do not mean this as a criticism of the maintainers. The people who work on these libraries are doing it in their spare time. They have very limited resources. If you're in academia, you're not getting credit for work on open source libraries much of the time. And so just don't have time to work on performance. And also they're trying to support general purpose use cases, and so that can work against performance. Your code is specialized, and so you might be able to optimize it for your specific data and its specific properties. And once you've gotten rid of wasted work, you can also try optimizing your code for modern CPUs. And this is an example from an article on my website where we want to threshold some data. We want to reduce the noise. Anything below a certain noise level in the image, you want to set to 0 because it's just noise. So you can see there's 2 versions here, one with NumPy and one that's written with Numba, with a code that's written specifically with understanding of how modern CPUs work. They use a lot of tricks to go really fast, but you have to understand them to actually get that speed. And you can see you get a really big speed up. And on your computer, it might be a little bit different, and it might be quite as good, but you can get really significant speed ups just by tuning your code to, based on how CPUs work. to take advantage of things like instruction level processing and SIMD and other CPU features. And this is the thing you do all the way at the end, but even here you can still get significant speedups. And all the speedups you get from architecture down to this level of tuning are cumulative, and so you can get the multiplicative. So you can go much, much faster than your original code if you work on all these levels. So you probably don't want to parallelize your code as first thing. Sometimes it's not possible at all, or only partially possible. It can sort of obscure the fact that you're using inefficient code, which might be, in some cases, very easy to fix. Like you might be able to spend an hour and have your code be 4 times faster, 10 times faster, or not. It depends, but sometimes you can. You should check. And if you're trying to lower costs, like if you want to spend less money on computation, parallelism does not help. On the other hand, if you optimize your code first, it will reduce your computing costs. It is possible. Your code is quite often less efficient than it could be. The dependencies you rely on, the libraries you're using, are often less efficient than they could be. You can submit patches to open source projects to speed them up. You can write your own version of the algorithm that's tuned to your particular requirements. And if you think about your architecture from a perspective of optimizing it, it may also give you more opportunities for parallelism. So Polars, because it has in lazy mode, because it has the query planner, it can also use that to add parallelism in a way that'd be much more difficult in pandas. But you still want to parallelize your software. If you're using your local computer has a lot of cores. Like even cheap laptops these days have 4 CPUs cores. So your software will run faster without spending any more money. It's still worth it for cloud computing. If optimization isn't enough, like at least you'll get results faster. Or you can process more data without increasing your response time. So parallelism is very definitely worth it, but you should approach it second after optimizing your software. So that's my talk. I have a bunch of articles at pythonspeed.com. You can find the slides at pythonspeed.com/PyDataGlobal23. I work as a consultant, so I can help maybe speed up your software, and I'm working on a book focusing on the last 2 levels of optimization I talked about, getting rid of unnecessary work and tuning for modern CPUs. And please email me with any questions you may have.
That's wonderful. Thank you for the talk. Folks, we got a few minutes left, I believe. Where's my clock? There we go. Yeah. If there's any questions, feel free to put them in the chat. And we'll see what we can do. There's a question here. Is there any scope for interoperability of Python with C, C++, or even Rust as a strategy for optimizing Python algorithm?
Yeah, so the question was, can you speed up with low-level code? And yeah, like in general for this kind of processing, like if you're processing lots of data, you pretty much want to be using a faster low-level language like Rust or C or Python or Numba. If you look back at my examples, they're using Numba, which is a just-in-time kind of sort of compiler. Basically, it's giving you, it's equivalent to writing stuff in code in C or Rust. It's compiling to machine code. And that's part of the speed up, but only part of it.
Awesome. And I see another question I may have missed. Did you already answer? Does your cost analysis in the limit number 1 only apply to on-prem CPU costs?
So if you look, there's 2 examples there of both on-prem and cloud. And in cloud, it scales linearly. So if you want like 4 times as many cores, typically you'll pay 4 times as much. So you can pay 4 times as much and run in a quarter of the time, and it just balances out. And so parallelism does not reduce your costs. It gets you faster results if you have perfect parallelism, but it does not reduce your costs. As soon as you don't scale perfectly with more CPUs, you actually end up paying more. But yeah, you can't save money by using more cores typically.
Interesting. Another question, and I think we got time for 2 last ones here. So do you have any recommendations for profiling tools?
I've created a profiler of my own, SCIA graph, skygraph.com. It's also linked to my website probably. But it's commercial and does memory and performance profiling. For open source, Memray is a great memory profiler. PySpy or Austin are great profilers for Python programs, and they profile down to native code. And then once you're down to like optimizing native code, you want to use things like Linux perf or other tools, platform-specific tools. So it sort of depends on what level you're profiling at.